We'll start by looking at graphs of the simplest types of polynomial functions, which are of the form with just one term ax to the n. Just as it was the case with quadratic functions, the coefficient a in f of x equals ax to the n determines how wide the graph is. If the absolute value of a is greater than 1, that implies that f of x equals ax to the n is going to be narrower, which means vertically stretched compared to f of x equals 1x to the n. And if the absolute value of a is between 0 and 1, that means f of x equals ax to the n is going to be wider or vertically compressed relative to f of x equals 1x to the n. All other forms of transformations of functions which we have learned about apply to functions of this form as well, because after all, they are what? Functions, right? So let's review them real quickly. Recall that if we're given the graph of a given function, in all these graphs here, the reference function is going to be in dotted format. Then to apply this kind of a transformation to get the graph of this function, for example, for a positive value of k, to get the graph of f of x plus k, we would just take the graph of f, which is shown here in dotted format, and move it k units up. To get the graph of f of x minus k, if you recall, we just take this and move it k units down. To get the graph of f of x minus k, we're going to do a horizontal translation and grab the graph of f and move it k units to the right. Remember, if it's x minus k, as long as k is positive, that's going to be a movement to the right. If it's x plus k and k is positive, that's going to actually end up being a translation or movement to the left. Now, do note that for translations, which is what all of these are called, that's called an upward vertical translation, downward vertical translation. Then we have a rightward horizontal translation and a leftward horizontal translation. For all of these translations, the basic shape of the graph, the original reference graph, does not change. Next, we had stretches and compressions, if you recall. They're collectively referred to as dilations. These do change the shape of a graph. And if we just have a simple, if we have the graph of f, again, all the reference functions are shown here in dotted format. To get the graph of k f of x, as long as k is greater than 1, we're going to basically vertically stretch the graph of f of x by a factor of k. Notice that when you vertically stretch a graph, you actually end up horizontally compressing it, right? So keep that in mind. If you have g of x equals k times f of x, but k is between 0 and 1, to get the graph of g, what we would do is take the original graph and do a vertical compression, right? Notice that when you vertically compress a graph, you're actually going to horizontally expand it, right? And stretch it. When you have f of kx, we're going to do a horizontal stretch if the factor k is between 0 and 1. So some fraction between 0 and 1 or some decimal. Doesn't have to be a rational number either. Any number between 0 and 1. Then the graph of f of x will be horizontally stretched by a factor of 1 over k. Okay? Now, notice that the y values remain the same under this transformation, but each x gets sent to x over k, right? And finally, if you're looking at g of x equals f of kx with k greater than 1, that's going to be an actual horizontal compression of the graph by a factor of 1 over k. A similar situation with what gets sent to what as we had in the previous case. Now, for this one, notice that the y values again stay the same. It's the x values that get changed. All right. So this is again review. We've seen all this before. I just wanted to quickly remind you of these transformations, and there's a couple more. The reflections, right? Here we don't deal with any kind of a constant k. Here we have the graph of f shown here in dotted format, some reference function, and we want to know how to get the graph of negative f of x. Well, basically all the y's are going to be switched to what? Negative y. So the whole thing gets flipped over, right? This is a reflection of the graph of f of x, the dotted graph, across the x-axis, okay? And if you have f of negative x, basically the y's stay the same. Notice the y values are the same for each point, but the x's get sent to negative x. So that's why you get a reflection across the y-axis, right? Reflection of the reference function with respect to the y-axis. All right, in this graphic, we're looking at various even whole number powers of x, starting with x squared in red, right? Now look at the graph of x to the 4. This would be easy to graph. Just make a table of values, right? Make sure to have some negative values and some positive values. You know these are even functions, so their graphs are going to be symmetric with respect to the y-axis, right? Notice that as the powers increase from 2 to 4 to 6 to 8, the general shape doesn't alter too much, but it does get what? Flatter, right? Notice. And of course, if you do x to the 10, it'll even be flatter, etc. So basically, they take a little bit, as the powers increase, it takes a little bit longer to get to this 1 point or this negative 1 point. But then right after that, it really takes off. The ones with higher value exponents increase much faster once they cross this point, right? And of course, that makes sense if you just plug in the numbers, and it's because of the way that these numbers between 0 and 1 behave, right? They behave a little bit differently from these numbers to the right of 1, right? So that's why this difference exists. Now, we'll next look at what happens if n is odd. But also notice that here we're dealing with positive values of a. In fact, we're dealing with a equals 1, right? If we were looking at the negative version of these, of course, they would just be flipped across the x-axis, right? There will be a reflection of these graphs with respect to the x-axis. Now here we're looking at the graphs of ax to the n when n is odd, an odd whole number greater than or equal to 1. Looking at, basically f of x equals x itself to the power of, here's when n is 1, right? We just get a straight line, but for every power after that, whether it's cube or the 5th power or the 7th power, etc., you are going to get this familiar cubic shape, right? Where in the green. But again, just like in the previous slide, notice the higher the exponent, the flatter the graph will become near 0, 0, right? Now, again, these are the positive cases. We can also look at the what happens when the coefficient is negative, and of course, they will be reflected, correct, across the x-axis. All right, so here I've graphed the negative versions of these. So if this is x, the one in dashed here is negative x. This is the green here, solid green, is the graph of x cubed. The dashed green is the graph of negative x cubed, etc., right? So notice that with each of these, the dashed correspondent or the negative version is going to be a reflection with respect to the x-axis. So what that means is the part that's above the x-axis is going to flip over to below, and the part that is below the x-axis is going to flip over to the top, right? because all the y values are going to be changed to their opposites, right? So whichever part is now above the x-axis is going to fall below, and the part that's below the x-axis fall above. Same with the green. See, the part that's above the x-axis comes down below here, and this part that was originally below the x-axis flips over to what? The top. And that's true for all the cases. All right, so that's what basically a reflection with respect to the x-axis does, right? Changes all the y values to their opposites. All right, next we want to take a look at the graph of f of x equals x to the 5 minus 3. We also want to determine the domain, range, intervals of increasing and decreasing for it. So notice this is going to be just a simple vertical shift, right? We're going to take the graph of x to the 5 itself, shown here in red dotted format. Notice that it is quite flat near 0, 0 compared to x cubed, right? That's the only difference. Otherwise, they look pretty similar, x to the 5 and x cubed. And we're going to just grab it and move it 3 units down. If we wanted to actually do a graph by hand, which is pretty accurate, we would simply just make a table of values, just like we have here, and we would just plot the points, right? So here, you can see each y value is just going to be 3 less than the corresponding one for the reference function. The reference function here being r of x equals x to the 5. And that's basically all there is to it. Now, as far as the domain, of course, the domain part for any polynomial function is easy. Remember, polynomial functions are just made up of terms, each of which is just some constant on sometimes some whole number power of x. So there is no x value or real number that you can plug in to get you in trouble. So the domain for all polynomial functions is basically the set of all real numbers. So if you want to write that as an interval, we'll say the domain is equal to negative infinity to infinity, the interval from negative infinity to infinity, and the range, as it turns out, if the leading term or the highest degree term has a odd exponent, then the range is going to be all real numbers as well. These functions will eventually assume all positive and negative real number y values as well. So the range is going to be negative infinity to infinity as well. So where is this function increasing? Look at it. Look at whether you look at the reference function or the actual function itself that we're graphing. Notice it's always increasing, right? It's never there's never a point where this function stops increasing. So for the purposes of all our class, we can say it is increasing on negative infinity to infinity. Now, just that, because that fits the definition of what we mean by increasing, because we said that a function is increasing if a less than b implies f of a is less than f of b, right? Now we can see that this holds for the function across its domain, but an argument can be made that at 0, 0 itself, it's neither increasing nor decreasing. Okay, so once you get into calculus and handle this at a higher level, you may be excluding 0 from the interval on which it is increasing. But for the purposes of our class, we can say that this function is always increasing. Okay. And that is because in our class, we're concerned whether a function is increasing over an interval. Whereas when you get to a calculus class, you'll be concerned about whether a function is increasing at a given point or not. And in that case, we can get into more detail, and then 0 would be excluded. But for as far as intervals of numbers are concerned, we can say that this function is always increasing. And clearly the function is never decreasing. Okay, let's go ahead and move on. All right, next we want to take a look at the graph of f of x equals quantity x minus 2 to the power of 6. And we'll also determine domain, range, and intervals of increasing and decreasing for this function. Now, here we show the reference function in red, and that's just x to the 6, right? The reference function is r of x equals x to the 6. As you know, it looks quite a bit like x squared, except it is flatter right around 0, and which is also its x-intercept, by the way. And we know that the kind of transformation we need when the change is happening at the x level is going to be a horizontal shift, and we know that if this is negative, there's going to actually be a shift to the right. So we're going to take the graph of the red graph and move it 2 units to the right to get the blue graph, which is the graph of the function we're interested in. And that's basically all that is involved for graphing. Now, of course, if we want actual points, we can use a table of values, and that's easy to create this table and plot them. And you can see you would want to graph this obviously not to scale if you're going to be using this kind of a y value, correct? All right, what about domain and range? Now again, this is a going to be a polynomial function, so domain is just going to be all real numbers, right? And the range, however, notice when you raise an expression to the power of 6, you're never going to end up with a negative number. Every number you get will be non-negative. So that's why all the y values associated with either the reference function or the translated function are going to be either at or above the x-axis, right? So therefore, our range is going to be all non-negative reals. So our domain is going to be the interval from negative infinity to infinity, but the range will be the interval from 0 to infinity. Again, that's of course because raising to the power of 6 will not result in any negatives. All right. And notice the function, whether we look at the reference or the actual function we're looking at, we're going to be answering questions for the blue one. So let's look at that one. Is decreasing from negative infinity all the way up to 2, right? So we say decreasing on negative infinity to 2. And it's going to be increasing from there on, right? So the interval where it's increasing, it's from 2 to infinity. Now we don't include 2 itself in either one of these two intervals, because at 2 it's really neither increasing nor decreasing. And that's basically how we handle that graph. All right, next we're going to take a look at the graph of a function which will involve multiple transformations. The function is f of x equals negative 2 times quantity x minus 2 cubed plus 4. Notice that because of the minus 2 here, the reference function, which is r of x equals x cubed, is going to get moved 2 units to the right. Because of this plus 4 here at the end, it's going to get moved 4 units upward. Because of this factor of 2 here, it's going to get vertically stretched by a factor of 2. And because of the minus, it's going to get reflected around its new center line, which is going to be here. So the line y equals 4. So when we do all of that, then we obtain the graph of the blue function from the graph of the reference function, which is shown here in red. All right, and if you want some values, of course, it's easy. We make a table of values. Just pick some x values and find the corresponding f of x values. I've shown them for the reference function here as well for comparison, okay? And that's basically how we would graph that particular polynomial. Now notice you may be thinking, but look, this is not in the form we're used to, ax to the n plus, you know, an minus 1, x to the n minus 1, etc. But notice that if you sit here and multiply that out, that's just x minus quantity x minus 2 times quantity x minus 2 times quantity x minus 2, and then clean it up, you will get that standard form that you're used to. So it's a modified form of a polynomial function, that is. Okay, so make sure you understand that and we'll proceed. Okay, so let's go ahead and take a look at some general facts about graphs of polynomial functions. We know that the domain of all polynomial functions is the set of all real numbers R, which in an interval format we write interval from negative infinity to infinity. The range of odd degree polynomials, as we have seen, and we can see in these three graphs, is also going to be the set of all real numbers, right? These do take on all y values eventually, right? So now the range of even ones, right, as we have seen, we can see in these two examples, or we've seen before, they're always going to be more limited compared to the odd ones, right? And there will be some constant k where the range is going to be everything including that number and numbers above, or including that number and numbers below, as in this case here. So yeah, that is generally the way that these polynomial functions behave. Do note that even degree polynomial functions describe graphs whose ends both point up or both point down. Here you see they're both pointing down. Here you can see both pointing up. With odd ones, you get endpoints that go in opposite direction. One end goes, if one end goes to positive infinity, the other one is going to go down toward negative infinity as far as y values are concerned. And you can see that here as well. This end goes this way and this end goes that way. Again, this end is going toward negative infinity for y values, and this one is going toward positive infinity. But notice with evens, they both are going to point in the same direction. Okay, when it comes to understanding graphs of polynomial functions, one of the topics that we need to understand is that of tangency. Now, the tangent line, or simply tangent to a plane curve at a given point, now, if it exists, is the straight line that touches the curve only at that point. So you can see here we have a straight line, and it's going to be tangent to this curve, because it's the only point of intersection is going to have with this curve is going to be that point on the graph that we can see right here. So we say this line is tangent to this curve at that point. Okay, now you'll understand why it says if it exists in a minute. Two other topics of interest to us are smoothness and continuity. Now, the graphs of polynomial functions are both smooth and continuous over their entire domains, which is the set of real numbers. Now, smoothness refers to the fact that there are no points at which the graph of the function does not possess a well-defined tangent line slope. So you can see this would be a smooth curve, because at every point you can draw one well-defined tangent line, right? Like the one we just saw on the previous page. And you can do that for every point on this graph, right? Now, with this graph right here, which of course is not a polynomial graph, this graph is related to the absolute x function, the absolute value function. Notice that at this point right here, which is 3, there is no well-defined function to the graph of, I mean, a well-defined tangent line to the graph of this function at that point. Because for one thing, there are two kinds of problems. There are too many lines you can draw that only intersected at one point, right? At that one point. So one is not well-defined, because if it's going to be well-defined, it should be unique, right? The other problem we face is that there will be a couple of lines that touch this graph that would intersect with infinitely many points, right? So this is not considered to be a smooth point for this graph. So there's no well-defined tangent line at x equals 3. Now, continuity refers to the fact that there are no gaps or points of undefinedness in the domain of the graph, right? So, for example, for this graph, you can see there are no gaps or points of undefinedness. So we say this is continuous everywhere, right? Well, as if you look at this piecewise defined function, it gets split up right there. So at x equals 0, we say this function is discontinuous, and that's called a point of discontinuity. Now, polynomial functions don't have any of these situations here on the right. They're both smooth and continuous everywhere. One way of thinking about continuous is that if you were to draw it with a pencil, you would never have to take your hand off the paper to be able to graph the whole graph, right? Of course, remember, this goes on forever on this side and forever on that side, so you would need infinite time, and you would still not be able to finish the graph, but you get the general point of what I'm saying. And the same doesn't hold here, right? If I were graphing this function, I would be able to not lift my finger up to here, but then what would I have to do? Lift my finger and move it to a new place to continue the graph, right? So that's just an intuitive way of thinking about continuity. And of course, the intuitive way of thinking about smoothness is the fact that there are no jagged turns like this, right? All the turns are very smooth, and so you don't get any sharp corners anywhere in the graph. All right, so one other concept of interest to us is that of concavity. This concept usually gets covered in calculus. In precalculus, they usually just call it, the function wiggling, etc. But that's not a very professional way of dealing with this. So we're going to handle it the right way. We can talk about it. Since you know about tangent lines, you can understand what we mean here. Concave up, we say that a function's graph is concave up if all the tangent lines fall below the graph, like you see here, right? And it's concave down if the tangent lines lie above the graph. So concave up is basically the happy face look, and concave down is the sad face look, right? All right, and the last thing we want to talk about before actually getting into the graphing structure of these functions is turning points. Turning points are the x values at which a given function changes from increasing to decreasing or vice versa, okay? So you can see here, this x1 would be a turning point because this function is increasing all the way up to what? To x1. Then it stops, neither increases or decreases, and then does what? Starts decreasing. So this x1 would be considered a turning point. Now, the function, again, is increasing from negative infinity to x1. Notice it's decreasing between x1 and x2, so on the interval from x1 to x2. X2 itself is a turning point, so at that point we say it's neither increasing nor decreasing, but it does start increasing right after, right? So f is so x2 is a turning point, and the function is increasing on the interval from x2 to infinity. All right, so That's what we mean by turning points, where you either go from increasing to decreasing or from decreasing to increasing. All right, now let's consider what the effect of the multiplicity of a zero will be on the graph of a polynomial function. Now let C be a zero of a given multiplicity for the polynomial function f. Let's see what happens with different multiplicities. Now if the multiplicity is 1, the graph of the function is going to cross the x-axis at C0, right? The ordered pair C0. The graph does not turn. Notice if it's decreasing, it continues decreasing, and if it's increasing, it continues increasing. So it doesn't turn at that point, right? Now, the change in concavity cannot be determined without analyzing the slopes of the tangent lines before and after C0 when the multiplicity is 1. So that is going to be handled in calculus. But if the multiplicity is even, then meaning the multiplicity of the 0, right? Then the graph is going to be tangent to the x-axis at that point. Think what? Think x squared, right? Or negative x squared, right? For that matter. The graph does not cross the x-axis at the x-intercept, right? When the multiplicity is even. Notice that the graph does turn, right? In both of these cases, I'm showing you 2 examples here of each. So, and notice that it does not change concavity, right? It's got the happy face thing going up to here, and then after that as well. So it does not change concavity in either of these 2 cases. Now, if the multiplicity is odd but greater than 1, so meaning what? 3, 5, 7, etc., right? The graph is going to cross the x-axis just like it did with multiplicity 1, right? And the graph is going to be tangent to the x-axis at C0. We didn't have that with x equals 1, right? But with x3 or higher, the graph is going to be tangent to the x-axis at that point, meaning it's going to look like that. All right, and the graph does not turn at C. Now, here really a more correct way of putting it would be that the x-axis, which is the line, is actually tangent to the graph at the point C0, right? That would be like a better way of thinking about it. Now notice the function, the graph of the function will not turn at C0, right? So this should be C0s, right? So it doesn't turn at C0, and meaning if it's increasing, it continues increasing. If it's decreasing, it continues decreasing thereafter as well. Now, but do notice that for these, the graph does go from happy to sad or from sad to happy, right? I mean, what I meant is happy to sad in this case, the one down below, and sad to happy here, right? So it does go from concave up to concave down here, concave down to concave up here. So it does change concavity at C when the multiplicity is what? Is some odd number greater than 1. All right, the turning points theorem, which comes next, tells us that a polynomial function of degree n has at most n minus 1 turning points, with at least 1 turning point between each pair of successive zeros. Now, this makes a lot of sense when you look at a simple example like this, right? Notice here's a cubic polynomial with the maximum number of zeros possible. Remember, an nth degree polynomial is going to have at most n distinct zeros, right? So notice this cubic or third degree polynomial has all the maximum number of zeros, which is 3, right? But notice that because of that, at the most it can have 2 turning points, right? Because here's one turning point, right, where it's going from increasing to decreasing, and here's another one where it's going from decreasing to increasing. What would happen if there were another turning point? That means what? That means there would be what? Another zero somewhere down here, right? Or if there was another one on this side, same thing, right? So it would contradict the fact that you have only what? 3 zeros here. So this polynomial with 3 zeros should have at the most 3 minus 1, which is what? 2 turning points. This point also makes sense because there should be at least one turning point between each pair of successive zeros, because look, you have 1 0 here. Notice this function is increasing while going through that 0, right? And what happens? Here's the turning point. So here's the other 0. If there were no turning point here, what would happen? This would just keep going up, and it would never come back down to hit the x-axis. So it would be impossible for there to be another 0. So that's why there should be at least one turning point between each pair of zeros. Same here with these two zeros, right? It's going down like this, right? If there were no turning point, which like there is here, this would keep going down, and it wouldn't come back up to give us what? This other 0. So that would be a contradiction as well. All right, so we can see why this theorem makes sense intuitively. If you're going to write up the proof, it would be similar to what we just discussed anyway, right? This would be a good case of a proof by contradiction. All right, now an important fact about end behavior. As one would expect in a polynomial like this, a n x to the n plus a n minus 1 x to the n minus 1, etc., this highest degree term is going to be the dominant term of the polynomial. So the end behavior of this term is going to dominate all the other terms, and it's going to be the same end behavior as the entire polynomial. So the end behavior of the graph of a polynomial is determined by its highest degree term. So for if it's written in this standard form, it's going to have the same end behavior as f of x equals a n x to the n. Okay, so here we want to describe the end behavior of this function, 2x cubed minus 12x squared plus 22x minus 12. You can see that the sorry, let's try that again. The leading term here is let's just call it L of x equals 2x cubed, right? So the end behavior of this polynomial is going to be exactly like the end behavior of 2x cubed. Now we know that 2x cubed is very similar to x cubed, right? Except it's a little bit vertically stretched, right? Well, by a factor of 2 to be exact, right? So we know the end behavior is that as x approaches infinity, so as x values get larger and larger, what happens to the y values? They get larger and larger, right? So the f of x, the y equal f of x values also approach infinity. And as x approaches negative infinity, as x values become smaller and smaller, right? What happens to the y values? They also follow suit, right? So as x approaches negative infinity, the y equals f of x values also approach negative infinity. All right, and that's how you would determine the end behavior of that function. All right, how about the end behavior of this function? F of x equals 8 minus 4x plus 2x squared minus x cubed. This, of course, is not written in descending order. If you were to do that, it would look like this. F of x equals negative x cubed plus 2x squared minus 4x plus 8. So the leading term function for this function is negative x cubed. That means this function's end behavior is going to be exactly like the end behavior of negative x cubed. So here we have negative x cubed. Remember, x cubed looks like this, which I'm just tracing. So you reflect it with respect to the x-axis, and you get the graph of negative x cubed. So these are some basic graphs you need to have in your repertoire. you shouldn't have to sit there and go through a bunch of plotting to get some basic graphs, right? So you should know, for example, the graph of x squared looks like this, right? The graph of, let's do better. The graph of negative x squared would be what? Just that upside down, right? You should know that the graph of, for example, x cubed looks kind of like this, right? And the negative x cubed, everything gets reflected, so it'll just be kind of like this, right? Etc. So these basic graphs you should have in your mind as we proceed. All right, so what is this end behavior that we see? So as x approaches infinity, as x values get larger and larger here, what happens to the y values? They get smaller and smaller. So the y values go toward negative infinity. And as x approaches negative infinity, what happens to the y, which is what we're calling the f of x? So just think of that as y, right? What happens to the y values? They're getting larger and larger. So y approaches positive infinity. All right, so that's the description of the end behavior for that polynomial function. Okay, so here's a summary of the end behavior of polynomial functions with lead term ax to the n. Now, if n is odd and a is greater than 0, right? Basically, think x cubed, right? That's what I want you to have in your mind. They're going to behave like x cubed. So that means as x approaches infinity, f of x is going to approach infinity, right? And as x approaches negative infinity, the y values are also going to approach negative infinity. For the example is shown here of a function that does that. If n is odd but a is negative, right, it's going to basically behave like what? Here you're going to think, so if here you were thinking x cubed, here you're going to think negative x cubed, right? It's going to behave like negative x cubed. So as x approaches infinity, the y values are going to approach negative infinity, and as x approaches negative infinity, the y values are going to approach infinity. All right, so if n is even but a is positive, then it's going to be this kind of a scenario. I want you to think x squared, basically. So how does that behave? Well, just like this, right? As x approaches infinity, y is going to approach infinity, and as x approaches negative infinity, y is going to approach infinity as well. So remember, these both point the same direction. All right, and finally, for n even and a being negative, I want you to think negative x squared, right? And as x approaches infinity, y goes toward negative infinity, and the same for x approaching negative infinity, y is going to approach negative infinity as well. Here is an example. All right, for these two. All right, so that's basically it for the summary of our end behavior. All right, so here's a good problem. I want you to pause the video and see if you can match these to the right graph based on your understanding of end behavior, okay? And then come and see if our answers agree. Okay, so as you can see, let's say for this first function, right? Its lead term is right there, so we're only focused and worried about this, right? Notice that it is an even exponent with a negative coefficient. So if you remember, this is the one where we would like to think what? Negative x squared, right? So this is the kind where we're going to have this scenario, right? So which one of these would fit, right? There's only one. I think I heard you say this one, right? All right. How about for B? Well, the lead term is right there. It's 4x cubed. So basically think x cubed, right? So that means this scenario, right? So which one of these satisfies that? I think you said this one, right? And I agree. All right. How about part C? Well, this is going to be the lead term right here, 3x to the 4. So we know that it's an even exponent and a positive coefficient. So we're going to think what? Similar to x squared, right? That's going to be the scenario. So which one of these do you think satisfies? Did I hear you say the first one? I agree. Okay. And how about part D? Let's see. The lead term is negative x to the 7. That's the only one we're worried about. It's an odd degree, so we know the ends are going to go in opposite directions, right? And the coefficient is negative, right? So it's going to be, what's the function you're going to think? You're going to think negative x cubed, right? So basically this scenario, right? So there's only one like that here, and it's the only one that's left over, right? So this one would be D. All right, think about that. Make sure that totally makes sense to you. Again, when it's even, they're both going to be either going down like this together when the coefficient is negative, or they're going to be going up like this when the coefficient is positive, right? Whenever the exponent is even on the leading term, right? And with the odd ones, right, either they're going to act like x cubed, so falling to the left, rising to the right, or like negative x cubed, rising to the left, falling to the right, okay? All right, so we want to take a look at the graphing techniques for trying to graph these polynomials. We've discussed several characteristics of the graphs of polynomial functions that are useful in graphing them by hand. A proper graph of a polynomial function should have all of the following characteristics. It should show all of the x-intercepts of the graph, basically zeros of the function, as well as the behavior of the graph at those zeros. Okay, we discussed what happens depending on the multiplicity of those zeros, remember? And then it should have the y-intercept. It should show the sign of f of x within the intervals formed by the x-intercepts, right? Whether like the function is above the x-axis or below the x-axis, etc. Meaning whether the y values are positive or negative. And we should have enough of the domain to show the end behavior of the function. To that end, we'll use a three-step process to graph polynomial functions of the form f of x equals a n x to the n plus a n minus 1 x to the n minus 1, etc. With a n not being 0, because otherwise it would no longer be an nth degree polynomial, right? All right, we will find all the x-intercepts by solving the equation f of x equals 0 for x. Then we'll go ahead and find the y-intercept. Remember, there's only one y-intercept because these are functions. And all we have to do is find f of 0. So we let x be 0, and we find out what the y values is, and that'll tell us where the graph will cross the y-axis. Notice that for polynomials in this standard form, when you plug in 0, all these terms that have x's in them are going to get zeroed out, right? What's the only thing left? A0. So this is always true. F of 0 is just going to be the constant term of the polynomial, okay? Then we'll apply all the knowledge we have gained about crossing the x-axis, turning points, or just turning, and changes in concavity, etc. And we'll also plot some of the selected points, which we call test points, and we'll also make sure to show the end behavior to come up with a decent graph of these functions. All right, so finally, we're ready to go ahead and try to handle a graph completely. Now, I put the end product here because you really don't want to see me do this by hand on a touch screen. But the main thing is going to be to find out exactly why it looks this way. So that's the easiest part. So let's go through the process completely and see what we need to do. Remember, the three-step process was that we're going to first find the x-intercepts, right, by setting the function equal to 0. And then we're going to find the y-intercept by just finding f of 0, or we know it's going to be just a constant term. And then we'll look at the intervals created by the x-intercepts and try to graph the function, okay? So let's go ahead and find the zeros. We're going to set 2x cubed plus 5x squared minus x minus 6 equal to 0. Now, we know that the values of, if p over q is a 0 of this function, we know that p should come as a factor of 6, right? So it's going to be plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. And q should be a factor of 2, as long as this is in descending order, which it is, right? So that's just going to be plus or minus 1, plus or minus 2. So that means p over q values are going to be, remember, we're just going to systematically divide, right? So plus or minus 1, plus or minus 2. The correct thing to say is positive or negative, right? But let's face it, plus or minus sounds a lot better, right? And then, just so you know, it is more appropriate to say positive or negative. And then positive or negative 6. Now we're going to divide by positive or negative 2, so positive or negative 1/2. Positive or negative 1, which is already covered. Positive or negative 3/2. I'll mix it up between positive, negative, and plus minus. And then positive or negative 3, which is already covered. So here are all the possible rational zeros. So we'll just start with the nicest of them, which is 1. Hopefully we'll get lucky and it'll be a root. So we're going to go ahead and divide the polynomial by x minus 1 to see if the remainder is going to be 0, right? And then use the remainder theorem and the factor theorem to go from there. So 1, 2, the coefficients of the polynomial are 2, 5, negative 1, and negative 6. We're going to use synthetic division, and the 2 drops down. 1 times 2 is 2. 2 and 5 gives us 7. Times 1 is 7. Minus 1 is 6. And 1 times positive 6. 1 times 6 is 6, and 6 and negative 6 gives us 0. So this verifies that this is going to be f of 1. So that means 1 is a 0 of this polynomial. So I should be able to now handle the rest because it was cubic. So we know this is going to be a quadratic quotient. So we can write f of x as x minus 1 times, that's constant, that's x squared. So 2x squared plus 7x plus 6, right? And now we should be able to factor this part, right? Worst comes to worst, we would have to use the quadratic to try to see how it factors out. So we get x minus 1 times 2x, and then x, and maybe 2 here and 3 here, right? That looks like it should take care of business. All right, so notice first times first is first, last times last is last. Inner and outer products do add up to the middle term, so we've done it correctly. All right, so now we're going to set that equal to 0. So let me just go ahead and get rid of that and turn this into the equation I want. So we get either x minus 1 is 0, 2x plus 3 equals 0, or x plus 2 equals 0 by the zero factor property or the principle of zero product, whichever name you like to use. So we get x equals 1, 2x equals negative 3, so x equals negative 3/2, or x equals negative 2. So that, as you can see, is where our zeros are, right? One is at negative 2. The other one is at negative 1.5 right there. And the last one is at 1 right there. Now, that's the first part where we find the x-intercepts. Now we'll go ahead and find f of 0. So the x-intercepts are basically 0, 1, 0, negative 3/2, 0, and negative 2, 0. For the y-intercept, we just find f of 0, which, as you know, is going to be very easy. All these 0 out, so it's just going to be negative 6. So therefore, the y-intercept is going to be the ordered pair 0, negative 6. We can see that here in the picture, okay? That's where the function's graph is going to cross the y-axis. All right, so let me go ahead and put these zeros in our table down here, which I've created to make it a little bit more organized. So we're only looking at zeros, so we're not going to need ordered pairs because we're only looking at the x values. So we have negative 2, negative 3/2, and 1. All right, so do notice from the factorization that the multiplicity of each of those zeros is 1. The graph crosses the corresponding x-intercept or not. Does it? Because when the multiplicity is 1, we know that the graph does cross. And you can see that in each of the zeros cases, graph crosses here, and it also crosses there, crosses the x-axis. So yes, yes, and yes. Does the graph turn at the corresponding x-intercept? If you remember, when the multiplicity is 1, the graph does not turn. You can always go back to that page if you like to check it. So we know that the graph does not turn when the multiplicity is 1 or odd in general, right? So for all of those, we can say no. And you can see that here as it crosses this 0 or this 0 or that 0. If it's increasing, it keeps increasing. If it's decreasing, it keeps decreasing, and again increasing. So it does not turn. Now we know that we can't determine whether the concavity changes or not when the multiplicity is 1, but we'll be able to find out once we look at the intervals and our test points and we plot some points in. All right, so the intervals of interest to us are going to be the intervals created by the zeros. So we're going to be looking at negative infinity to negative 2, and then from negative 2 to negative 3/2, which is the next zero, and then negative 3/2 to negative 2, to 1, and then everything after 1. So those are the intervals we're going to be looking at. So we'll just write them in here. So negative infinity to negative 2, and then from negative 2 to negative 3/2, and from negative 3/2 to 1, and then 1 to infinity. So we'll pick a test point from each of these regions, right? So from negative infinity to negative 2, we'll just pick negative 3. From negative 2 to negative 3/2, that's negative 1.5. So that's going to be a little bit harder to come up with. So we'll just take half the midway point. So negative 1.75. So from negative 3/2 to 1, now this is easy. Anytime the interval goes from a negative number to a positive number, there's always a very nice number in between, within, that zone where it's going to be very easy to work with, which is 0. Okay? And from 1 to infinity, we don't have to go far, we'll just use 2. Okay? So we're going to go ahead and plug these in to the original function. So we'll just bring a calculator up and plug in. Okay, so we want 2 times, we're plugging in negative 3. And we're going to go ahead and get out of the parentheses and square that. Cube that, sorry. And then you want to make sure to hit the right arrow to get out of the exponent position. And then plus 5 times, again, we're going to substitute x with negative 3. And then we're going to square that. And then minus quantity negative 3. We could have just written plus 3, but this is fine. And then minus 6. So we get negative 12. And now we're going to substitute negative 1.75, right? So the nice thing about this calculator is if you just double click or double tap it, it copies it, and then we can just go and replace all those negative 3's that we used with negative 1.75. All right, so the main thing is to make sure that you're careful to plug this in correctly. So I'm just going to always stop and double check, especially when it's something like negative 1.75. Okay. And we're good. Okay, so we get negative, actually positive, approximately 0.3. Okay, so now we will go ahead and substitute 0. This one we can do in our heads, right? That zeroes out, that zeroes out, that zeroes out. We get negative 6. We already had that point, right? And for the last zone, we're going to substitute 2. So we will once again copy that, and we'll just replace the negative 3's with 2's. Okay, and then we're ready to go ahead and calculate that. So we get 28. All right, so notice the sign of f of x in this zone. Remember, this is just a test point, but it's going to work the same way for all the points in that zone. So we know that from negative infinity to negative 2, the function is going to be below the x-axis, because the sign of the function is going to be negative. Between negative 2 and negative 3/2 right here, we know it's going to be above the x-axis because it's positive. Between between a negative 3/2 and 1, which is the next 0 is what I meant. Between negative 3/2 and 1, it's going to be negative, so it's going to be below the x-axis. And everywhere after 1, it's going to be positive, so it's going to be above the x-axis. So if we simply plot those points, right, and then go ahead and draw our line based on our information that we have, smoothly connect them, we'll come up with this graph. Notice that there are not going to be any sharp turns or anything like that, so this has to be done very smoothly. But this is going to be the general shape of the function that we are graphing. So we use pretty much all the information that we use. So just to complete this table here, remember the graph is going to be below, here is going to be above, again below, and above. So with all that information, we can get a pretty nice, accurate picture of the graph that we're trying to do. There are a few steps involved, but I mean, all of them are pretty simple steps and very logical, right? It makes sense why we do those things. All right, so that pretty much tells us how to graph this function. Make sure that you can start from scratch, go through all the steps by yourself before we proceed. Now this next one is a little bit nicer because it's already in factored form, okay? But I wanted to show you just so that we can get some points across. As far as the end behavior, for example, we see this negative is going to make a difference. Let's go back and take a quick pause and go back to the previous one. I want you to pay attention to the fact that the lead term was 2x cubed, right? So we knew the behavior of this function is going to be very similar to that of the end behavior is going to be similar to that of 2x cubed, which itself has an end behavior similar to x cubed, meaning this situation, right? Notice that we did have that scenario going falling on the left, rising on the right, okay? Now let's go back. Now we know that this is not given to us in standard form, but we can still get a good graph of this even with this form without needing to go to standard form. So notice that our zeros are very easy to find because it's in factored form. The zeros are going to be 1, 3, and -2, right? So we can put them in here already. Let me put them in order from small to large. It's nicer. So -2, 1, and 3. Now, the multiplicity of 1 is 1. The multiplicity of 3 is also 1. But the multiplicity of the -2, 0 is 2, right? All right. So we know that when the multiplicity is 2, the graph is not going to cross the x-axis. When it is 1, we know that it will cross the x-axis, right? All right. Let's take a quick moment to find the y-intercept as well. So we know the x-intercepts are 1, 0, 3, 0, and -2, 0. The y-intercept we find by finding f of 0. Now, it's not, this is the one thing when it's in this form that may be a little harder to find, because it's not just going to be the last term because it's not in standard form. So it's easy though. Just plug in 0 instead of x. So we get negative. Now, 0 minus 1 is going to be -1. 0 minus 3 is going to be -3. And 0 plus 2 is 2. So we get 2 squared. So -1 times -3, that's positive. 3 times 4 is positive 12. So the y-intercept is going to be the ordered pair Hang on a second. I'm pausing here because I just caught something. It's actually, this part is what's going to be positive 12. There's that negative on the outside that we have to consider. So it's -12. So the y-intercept will be 0, -12. Okay? And, all right, so what do we know as far as turning at the corresponding x-intercepts for these zeros, right? Notice that we know that when the multiplicity is 2, it does not, it does turn, sorry. But when the multiplicity is odd, it doesn't turn. So for even multiplicities, the function does turn. Take a look. It's increasing. Then it's what? After -2, it's decreasing. So when the multiplicity is even, yes, it does turn at the 0. When it's odd, no. Okay? Now, the only one that we can say something for sure about concavity is going to be the one with the multiplicity equal 2, because we know that when the multiplicity is even, the function does not change concavity. So notice it's concave down before and it's concave down after, right? So with these we won't be able to determine just from the given information. You'll be able to determine it in a calculus class. Here we'll just have to go with the points that we get in order to get a better graph, okay? All right, now that's because the multiplicity is 1. Had it been 3 or higher, we would have been able to determine concavity, okay? Because had it been 3 or higher, yes, it would have changed concavity, but we have only 1, so that's the indeterminate one as far as this class is concerned. All right, so what about the intervals of interest for us, right? The intervals of interest are going to be -infinity all the way to the first 0 on the left, which is -2. And then -2 to 1, and then from 1 to 3, the interval from 1 to 3, and then after 3. All right, so we'll pick a test point from -infinity to -2. How about -3? From -2 to 1, you know it's going from a negative to a positive, so you know 0 is going to be in there, so we'll pick that. And from 1 to 3, we'll pick 2. 3 to infinity, we'll just pick 4. Okay? Then we substitute. So let's go ahead and, as easy as this is going to be, actually, we can still make mistakes. So let's be very careful. So we want f of -3. Let's be a little systematic here. F of -3. That's going to be negative on the outside, and then -3 minus 1 times -3 minus 3 times -3 plus 2 squared. So we get -4 times a negative opposite of -4 times -6. -3 plus 2 is -1, and then squared. So basically we get -24 times 1, which is -24. Okay? And now we'll find f of 0. So plugging in 0, we know gives us -12. We already did that. Okay? We need f of 2. That's going to be the opposite of 2 minus 1 times 2 minus 3 times 2 plus 2, quantity 2 plus 2 squared. So we end up with the opposite of 1 times -1 times 4 squared, which is going to be a positive 1 times 16, so it's 16. Okay? And for f of 4, our last test point, we're going to get the opposite of 4 minus 1. Remember, we're just plugging in here, right? Whenever you see x, substitute it with 4. So we get the opposite of 3 times 1, and that's going to be 6 squared, which is 36, right? So we get negative 96, right? No, more than that. What's the 3 times 30 is 90, negative 108. Yeah, 90 and 18, right? So 108, negative 108. All right, so let's go ahead and put those into our table. So for f of -3, we got -24. For f of 0, we have -12. And for f of 2, we have 16. For f of 4, we have -108. So the sign here is obviously negative, negative, positive, and negative. So notice this is going to be only above the x-axis between 1 and 3, as we can see here, okay? The graph above or below, well, it's going to be below for all the negatives, right? And it's going to be above only in this region. Okay? So now, by plotting all the x-intercepts, the y-intercept, and then our test points. So we did -3, 0, 2, and 4. By plotting those points in and smoothly connecting the lines and making sure all our turning points are smooth, etc., we end up with this fine graph that you see here. Now, as far as end behavior, notice here we know we don't need to actually completely work it out to get a feel for what the lead coefficient, well, the lead term is going to be as far as power of x, because you're going to have an x here times x, that's going to give you x squared, and this is an x squared. So we know it's going to be like an x to the 4 or a 4th degree polynomial, right? Quartic polynomial, and because of that negative, this should behave like -x to the 4, right? So we know what -x to the 4 behaves like, because that itself is an even exponent. So basically kind of like what? Like -x squared. So we expected the end behavior to be that way as well. All right? So there you have it. That's how you basically go through and graph a polynomial in this format. Find your zeros, find the y-intercept, analyze them, right? Analyze what the zeros and their multiplicity can, the kind of information it reveals, right? And then set up your intervals, set up your test points, and then plot everything. Plot your zeros, plot the y-intercept, plot your test points even, right? For more additional graphing points. I mean, you've gone through the trouble of calculating, you might as well use them, right? And then smoothly connect them, remembering that graphs of polynomial functions are both smooth and continuous, and you'll end up with a great graph. Again, make sure you can go through all these steps on your own, and then we'll proceed. Okay, sometimes we're asked to go backward. We're asked to find the expression for a polynomial given the graph of the polynomial. We note that it's possible to reverse the process we utilized in the previous example and find a polynomial function from its graph if zeros and any other point on the graph are known. Suppose that, for example, you're asked to find a polynomial function of least possible degree having this graph, right? Which should look familiar to you. Given that the graph crosses the x-axis at 1, 0, and 3, 0, and -2, 0, we know the factored form of the function will have this form, right? A times x minus 1 to the 1 times x minus 3 to the 1, and we know that the multiplicity for that -2, 1 is going to be 2 because of the fact that it is not crossing, right? And it is turning. So we use that information to realize that the multiplicity on the -2, 0 should be what? 2. Now we find the value of a. Now remember, any function that any constant you multiply by those factors is also going to have zeros at those points. So the question is, which particular one should we use here? And we take this and we replace, we know the point 0, -12 is on this graph, right? So therefore, because remember f of 0 was -12, we figured that out. So what we do is we substitute -12 for f of x, and we substitute 0 for x, and then we simply solve this for a. So we get -12 equals 12a, so a equals -1, and now we know our equation is going to have exactly this form. So this is how we find a. We have to have one condition that's initially known. That usually is referred to as an initial condition. As long as we have that, we can get a equation. We can get an equation, an exact equation for a given graph. Normally, we do not write the 1, but that I wrote it there for emphasis. So when you want to present your final answer, leave that 1 out. Okay, you should be able to handle this one now on your own. Go ahead and pause the video and try it, and then come back. Okay. All right, so we can see our zeros here are at -6, 4, and 9, according to this graph, right? So we know that our polynomial can have the form f of x equals a times x minus the first 0, so x minus -6, which turns into +6. And this is a simple crossing, right? We don't with no turning, so we know it's just going to be multiplicity 1 here. And we also know it's 1 and not, for example, 3 or higher, because remember, the graph would be tangent to the x-axis if it were 3 or higher, right? So we know it's just going to be a simple 1 multiplicity there. And then times x minus the second simple 0 of multiplicity 1, so -4. And then times x minus another 1, which is 9, okay? Now we do see from the graph right here that f of 0 equals what? 108, right? So therefore, we're going to use that information to find the exact value of a. So we replace f of x with 108, and we replace x with 0. We're just plugging in this information, that for x and that for y, or f of x. So we get 0 plus 6 times 0 minus 4 times 0 minus 9. So we get 108 equals a times 6 times -4 times -9. So let's go ahead and multiply that out. So 6, we know this is going to end up positive, so we don't need to enter those negatives. So 6 times 4 times 9, 216. So 108 equals 216. A, divide both sides by 216. So we get a equals 1/2. All right, so now we're ready to go ahead and write our function. So we get f of x equals 1/2 instead of a times x plus 6 times x minus 4 times x minus 9, okay? Now, that is a perfectly good definition for that function. If it's asked for in standard form, you just multiply that out, right? So you would get f of x equals 1/2 times x plus 6 times, this is gonna, we're just gonna multiply these two out first. So that's gonna be x squared minus 9x and then minus 4x, so minus 13x plus 36. Now we just need to go ahead and multiply those two polynomials. You know me by now, I like to do those in a table. All right, so we get x cubed minus 13x squared plus 36x for the top row of our table. For the bottom row, we get positive 6x squared minus 60 and 18 is 78x And then we did 6 times 36. What was it? 108. So 6 times, let's see. 6 times 30 is 180. And 6 times 6 is 36, right? So 196. Check that. I mean 180 and 36. That's actually 216. So it didn't sound right to me. All right, so plus 216. Okay, so now we can say f of x is equal to x cubed. We can combine those two, right, to get what? Minus 7x squared. We combine these two. So let's see, what is 36 from 78? So minus 42x. And then plus 216. And don't forget, there's a 1/2 at the very beginning. So just think that whole thing needs to be divided by 2. So let's write the final form, standard form. 1/2 x cubed minus 7/2 x squared minus 21x, right? Plus 108. All right, so there it is in standard polynomial form, and there is the same function in factored polynomial form. All right, so there's another example of finding a polynomial given its graph, right? Okay, so make sure you can do that, and we'll move on. All right, here's the last one of these. We're going to find a polynomial function for this graph, right? Describing this graph. So notice this is going to be a 0 of multiplicity 1, right? But this one is going to be 0 of multiplicity 2 because it doesn't cross, right? And it does turn, so from decreasing to increasing. So we know that's the characteristic of a multiplicity 2. Because, well, 2 or higher, right? As for a 2 or higher even multiplicity. But it says of least possible degree, right? So we'll just go with 2. So we have f of x, which is going to be a times x minus the first 0. So x minus -5, which is just x plus 5, times x minus the second 0, but then we're going to square that one, right? Because of the multiplicity 2. The initial condition we have is given right there. F of 0 equals what? 9. All right, so instead of f of x, we're going to put 9. And instead of x, we're going to substitute 0. So we get 9 equals, this right here is going to be 9 times 5, so 45. Divide both sides by 45, you get a equals 9 over 45, reduces to 1 over 5, so a equals 1/5. So this time we get f of x equals 1/5 times x plus 5 times x minus 3, quantity x minus 3 squared. All right, so you could go ahead and multiply that out just like we did in the previous example. I encourage you to do it, but for the purposes of saving time, I'm going to leave that for you. But that would be very easy. Just work this out and then use a table to multiply this into it, and you'll be done. Then multiply the 1/5 by the product. All right, so there's a nice one. Let's go ahead and proceed. All right, so go ahead and recall from our previous lectures that if k is a zero of a function f of x, then all of the following hold, right? We know that f of k is 0, k is a solution or root of this equation, right? X minus k is going to be a factor of the polynomial. We can write that symbolically like this, right? So k is a 0 of f of x if and only if k is a root of f of x equals 0, if and only if x minus k is a factor of f of x. We know that we can add one more item to the list of k's talents, right? F of k is equal to 0 if and only if the ordered pair k0 is an x-intercept of the graph of f. All right, so here is a very important theorem of interest to us. It's called the intermediate value theorem for polynomials. If f is a polynomial function with real coefficients and a and b, that should be coefficients, and a and b are real numbers such that f of a and f of b have opposite signs, then there exists a real number c such that c is between a and b and f of c is 0. Now, the proof of this will have to wait till a calculus class. In general, the approach I have with respect to proofs in this class is almost every proof that you should be able to handle, we handle. The ones that need to be left for calculus, of course, we'll leave for that. And others we might skip, maybe ones that are not so consequential to our purpose in the class. So, but generally, we'll try to get plenty of proofs in here so that your mind can develop in the proper way. Basically, this is a very nice intuitive theorem. It says, look, if you have a polynomial, right, and you have a function a and b, so that the value of f at a is, for example, positive as it is in this graph, and at b it's the opposite, it's negative. In other words, the function is above the x-axis at a and below the x-axis at b. It's saying, look, this is totally implied by continuity, right? You can see where the graph, the proof would kind of go with this, but basically it's saying there has to be some point where this graph is going to cross the x-axis, meaning what? It's going to have a 0 between a and b. So if it's negative, positive here, or if it were negative here and then positive there. So as long as they have opposite signs, right? As long as you have a and b and they have two different signs, you know there's going to be a 0 of the polynomial between them. That's what we mean by the intermediate value theorem. So here we can use the intermediate value theorem to quickly show that this function is going to have a 0 between 2 and 3. Okay, so here's what we'll do. We'll go ahead and figure out f of 2, and then we'll find f of 3, show that they have opposite signs. That's all we have to do. So to find f of 2, I'll go ahead and use the remainder theorem. So I'll go ahead and divide by x minus 2 using synthetic division. So 1, negative 2. Notice descending order, no missing terms. So 1 comes down, so 2 times 1 is 2, and negative 2 gives you 0. 2 times 0 is 0. 0 and negative 1 give us negative 1. Negative 1 times 2 is negative 2, and 1 gives us negative 1. All right, remember, that's going to be f of 2. Now we find f of 3 in the same manner using the remainder theorem. I mean, we could just do what? We could just sit here and plug in, right? But hey, it's nicer if we use the theorems we've learned, right? They'll stick better. All right, so 1 times 3 is 3, and negative 2 gives us 1, times 3 is 3, and negative 1 gives us 2. 2 times 3 is 6, 6 and 1 is 7. Remember, that's going to be f of 3. So at this point, all we have to do is say, look, f of 2 is equal to -1, which is less than 0, and f of 3 is equal to 7, which is greater than 0. In other words, f of 2 and 3, f of 2 and f of 3 have opposite signs. Therefore, by the intermediate value theorem, there must be a 0 for f between 2 and 3. All right, so that's how you would apply the intermediate value theorem in this problem, okay? So very simple, but important conceptually. All right, let's go ahead and move on. All right, I do want you to make sure that you're careful not to misinterpret the intermediate value theorem. It states that if f is a polynomial and with real coefficients and a and b are real numbers such that f of a and f of b have opposite signs, then there exists a real number c such that c is between a and b and f of c is 0. We understood that in the last screen. What it doesn't say is that if f of a and f of b are the same sign for two real numbers a and b, there cannot be some number c between them when f of c is 0. So don't read too much into it. Here is an example. You have a and b. F of a is negative. Notice f of b is negative, yet this function does have a 0 between a and b. So all the intermediate value theorem does is that it says that if they do have opposite signs, you're guaranteed a 0 between them, right? But if they're not opposite signs, then you're not guaranteed, but there may be zeros between the two numbers anyway. So be careful when interpreting the intermediate value theorem. Okay, the last thing we want to talk about when it comes to graphs of these polynomials is the boundedness theorem, which says let f be a polynomial function of degree n greater than or equal to 1 with real coefficients and a positive lead coefficient. Suppose f of x is divided synthetically by x minus c. Then if c is greater than 0 and all the numbers in the bottom row of the synthetic division are non-negative, then f of x has no 0 greater than c. Now, the proof of this is not terribly difficult, but the theorem is not so consequential for us to spend a lot of time on it. But it is worth your time to look it up if interested. If c is less than 0 and the numbers in the bottom row of the synthetic division alternate in sign, with 0 considered positive or negative as needed, then f has no 0 less than c. So we will go ahead and apply this to one problem so you can get a feel for it, okay? Let's go ahead and take a look at an example. Here they're asking us, does f of x equals x to the 4 plus 7x cubed plus 5x plus 2 have any real zeros greater than 1? So, and when you have answered it, they want you to use a graphing calculator to approximate the real zeros of f. So here, notice that we have the coefficients. Now, this polynomial is missing a term, the square term. So be very careful when you set up your synthetic division. So we're going to put 1, 7. For the x squared term, we're going to put a 0. Be very careful with those missing terms. All right, and then we're going to do synthetic division. So 1 comes down. 1 times 1 is 1 times, and 7 is 8. 8 times 1 is 8, and 0 is 8. 8 times 1 is 8, and 5 is 13. Times 1 is 13, and 2 is 15. All right, so notice that this number 1 is positive, and the bottom row of the synthetic division resulting from dividing the polynomial by x minus 1 has all coefficients that are non-negative, we conclude that this polynomial has no zero greater than 1. So does f of x have any real zeros greater than 1? The answer is no. So now we're going to try to find the zero of this polynomial graphically, okay? So we'll go ahead and go to Desmos and graph that function. All right, so here we have graphed this function, and you can see there are two real zeros, and there are the values right there. So the approximate values of the zeros, negative 7.094 and negative 0.345. Notice that there are indeed no zeros greater than 1, as we have established. All right, so the last thing we're going to do for the day is look at a couple of applications and models of quadratic functions, and that should do it. So a storage tank for butane gas is to be built in the shape of a right circular cylinder of altitude 32 feet with a half sphere attached to each end, just like you see in this picture here. And of course, that would not be included in the calculation of this altitude here. If x represents the radius of each half sphere, what radius should be used to cause the volume of the tank to be 324 pi cubic feet? All right, so basically we need to come up with an expression which will be in the form of a polynomial for the volume of this tank, and then go ahead and set it equal to 324 pi, right? So here we have the volume of the cylindrical part, right, plus the volume of one full sphere, right? Half a sphere here, half a sphere there. So basically we're going to have, for the cylindrical part, right, you know that the volume is going to be the area of the base times the height, right? So pi r squared h. In this case we're using x for the radius, so we'll just say pi x squared h. That gives us the volume of the cylindrical part. And for the spherical part, we're going to have 4/3 pi x cubed, right? And we would like that to become 324 pi. Now, I have h here, but I know I can replace that with what? With 32. So let's go ahead and do that so we don't have to rewrite it. And I'll put it in the beginning because it looks nicer, right? So there is the volume for the entire tank, and we want that to equal to 324 pi. All right, so we're now going to go ahead and try to solve this. So let me move everything to one side. And put it in descending order. All right, so I noticed that I can get rid of the fraction easily by multiplying both sides by 3. So let's do that. So we get 4 pi x cubed. Now 3 times 32, that's 96, right? So we get 96 pi x squared minus 324 times 3. 3 times 300 is 900. 3 times 20 is 60. And 3 times 4 is 12, right? So we get 972. So minus 972 pi, and we need to multiply the other side by 3 as well, but that's just 0, so 0 times 3 is just 0. All right, so now I can see that there's a pi in all three of those terms, and there's a common factor of 4 as well, because 4 goes into itself, into 96 and 972. So we go ahead and divide both sides by 4 pi to make this look simpler. All right, so the first term becomes just x cubed. Uh, 96 divided by 4. That's like saying AD plus 16 divided by 4. So 20 and 4 gives us 24. X squared. 972 divided by 4. I'll just get help from our buddy here. 972 divided by 4. 243. Like so. Now you have enough ammunition in your repertoire to be able to solve this equation by finding the zeros of this polynomial based on techniques from the previous video. But that's not the purpose of this problem. So I'm going to go ahead and let you and myself both solve this graphically. So we'll go ahead and type this in to Desmos to see where our 0 is going to be. So x cubed, 24x squared minus 243. All right, so when we graph it, I just typed in y equals x cubed plus 24x squared minus 243. We can see there are 3 zeros, but we're dealing with the radius of a sphere, right? So we're only going to be able to accept the positive one. So we'll just click here to see that the x value is going to be 3. So now we know that the particular solution of this equation of interest to us is x equals 3, which means that's what the radius should be if we want the volume of the tank to be 324 pi. And that's all we really need to do, and we're done. Okay? So make sure you can run through something like that. For your own sake and practice, you may want to handle this with the techniques you have learned as well without graphing it on a calculator, and you'll come up with the same fact or the same 0 as well. All right, so let's go ahead and take a look at one more problem, and then we'll call it a day. All right, here we have the polynomial function defined by f of x equals pi over 3 x cubed minus 10 pi x squared plus 4000 pi d over 3, which can be used to find the depth that a ball 20 centimeters in diameter sinks in water. The constant d is the density of the ball, where the density of water is 1. The smallest positive 0 of f of x is going to be the depth that the ball sinks to. So we're going to approximate this depth for each material and then interpret the result, okay? Let's say we first look at a wooden ball with a density of 0.8, okay? So when we plug in 0.8 for d, right, we're going to end up with f of x is equal to pi over 3 x cubed. Don't forget, the x doesn't get substituted for, only the d, minus 10 pi x squared plus, now let me bring our friend up here. We're going to multiply we're going to multiply 4,000 pi by 0.8. So let me just take care of the 4,000 times 0.8. So we get 3,200 pi over 3. All right. So remember, the point is to find the zeros of this function, and it says the smallest positive zero of this function will be the depth that the ball sinks, right? So now we'll go ahead and for this one, we'll definitely do it using graphing. So we're going to now graph this on Desmos. Okay, so we have y equals pi over 3. Now, I think with Desmos, you can just put pi, and then it turns into pi. So pi over 3, and then make sure you hit the right arrow to get out of the denominator. So x cubed and then hit the arrow to get out of the exponent position, minus 10 pi x squared plus 3,200 pi over 3, right? All right, so let me go ahead and, now that we've copied it, let's double check. Pi over 3x cubed minus 10 pi x squared plus 3,200 pi over 3. Okay, so now notice that we have our first zero, positive 0 right there. So 14.257 or approximately 14.26. All right, so let's go back. So the smallest positive 0 was x, approximately 14.26. So remember, the ball itself has a diameter of 20 centimeters, right? So if it's only going to go down this much, that many centimeters, 14.26 centimeters is how much it's going to sink. That means what? That means it's not going to be fully submerged, right? It's going to be partially submerged at that depth. And of course, that means it's going to float partly above the surface, right? Some of it will be under the surface of the water, and some of it is going to be above, right? All right, yeah, most of it obviously will be under the water. About 5 and something centimeters will be above the water. So then we'll do the same thing for 2.2, right? D equals 2.2. So we have f of x So this was for part A, this is for part B. So we get f of x is equal to pi over 3 x cubed minus 10 pi x squared. Now I'll go ahead and calculate 4,000 times 2.2. So that becomes 8,800. I should have done that with my head, right? But here we are. So plus 8,800 pi over 3. All right, so now we're going to go graph this one, right? Notice the only thing that's changing, the last part is becoming 8,800 pi over 3. Okay, so we're just going to change the 3,200 to 8,800. All right. Now, notice here something interesting happens. We don't get any positive zeros. I'm going to try to bring this to a place where we can actually see it. All right, so here's a much better view of the graph, and you can see there's only one real zero, and it happens to be negative. So this has no positive real zero. So what does that tell you? This is not going to have any solution. Let's see if that makes sense. Look how dense this solid aluminum ball is, 2.2, right? We're trying to find the depth at which to which the ball sinks, and what's going to happen? That's so dense, it's going to just what? It's going to drown all the way to the bottom of the ocean, right? So that's why we don't actually get an actual solution for this, okay? Or even if we don't get that dramatic, we just know that it's going to be, below the surface, right? Okay. Now for part C, think about that, see what you think, what you're going to come up with. Notice this density is exactly the same as the density of the water. What do you think it should happen, and then find the actual result. So let's go ahead and plug it in, but think about it for a minute, right? So you get f of x equals pi over 3 x cubed minus 10 pi x squared plus the d here is going to be 1. So 1 times 4,000 is just 4,000 pi over 3. So now we're going to go back to Desmos, and we're going to change the last part to 4,000 pi over 3. All right, so notice this time we get a hit right there at exactly 20. So that means this ball, which is 20 centimeters in diameter, sinks exactly 20 centimeters. So you can see what that means. Because their densities were the same, this is why this happened. So it's going to submerge just perfectly so that the very top of the ball will what? Will be tangent to the surface of the water, right? So so remember, for part B, that was undefined. For this one, x was exactly actually 20 centimeters. All right, and that's a couple of applications for you. So that should pretty much take care of things for today. Make sure that you spend enough time with the video before starting the homework. As this stuff gets a little bit more involved, you definitely are going to want to get as much out of the lectures as you can before diving into homework, okay? All right, so that should do. You take care until the next lesson.